we welcome here Jankovič. He started his studies of physics at our university and then also did his master's here. Then he went over to do his PhD at University of Nova Gorica. And then today he's now working at the Institute of Physics of the Czech Academy of Sciences under the Physics for Future, co-founded by the European Union. And today he will present us what he's working on right now in Czechia. So yeah, so go ahead, Tai, and hope.
Thank you. Yeah. Hi everyone. Thank you, Samo, for inviting me, or to everyone. And yeah, I will be talking about a project that I have been working on together with Clément, Sergey, and Alexei. And this is related to a new class of astrophysical transients, which were detected in the centers of distant galaxies. And we are not really sure yet what these are, and I'll be talking about a specific model which could explain these phenomena. So first, I will briefly talk about black holes and supermassive black holes more in general. Then I will talk about these events, which are called quasi-periodic eruptions, or QPEs. I will address this from an observational point of view, and then talk a bit about different models. And then I will focus on the specific model, the star disk collisions model, the one that we are also working on. And in the last part, I will talk about the radiation-hydrodynamic simulations that we are performing. Now, black holes are astronomical objects characterized by a very strong gravitational field and an event horizon, so a region from which not even light can escape. And we can roughly divide them into three main categories depending on their masses: stellar, intermediate, or supermassive. But for my research, I'm focusing on supermassive black holes, so black holes with masses exceeding 10 to the 5 solar masses. These black holes are located in galactic centers, and they play an important role in the formation and evolution of galaxies. We can actually classify them into active and inactive black holes or galactic centers. And basically the difference is that the active supermassive black holes or active galactic centers, they have sort of a source of light which is near them for a long period of time, and this allows us to study them. For example, this can be either an accretion disk or jets, these high velocity outflows launched from the vicinity of black holes. And then we have inactive galaxies, so galaxies which don't have any strong source emitted for a longer period of time from their vicinity. They are in what we say a quiescent state. And for these black holes, we need some other ways of detecting them. And here, typically what's particularly useful are astrophysical transients occurring near them. For example, this could be stellar tidal disruption events, so events which occur when a star gets too close to a black hole and then is disrupted due to the strong tidal field, or also quasi-periodic eruptions, or QPEs. And these QPEs, these quasi-periodic eruptions, they were detected fairly recently in 2019. Here we see sort of what this detection looked like. So this is the galaxy where these QPEs were detected, and this is sort of the inset showing the X-ray signal. So these are basically bright X-ray flares occurring in the centers of galaxies in some quasi-period intervals. We can divide them into two classes, regular and irregular. And here we see an example of an X-ray light curve for a regular QPE. And these regular QPEs are characterized by bursts, flares, which occur roughly every 10 hours. And we also notice in this flaring, we notice a particular pattern. So we notice long, short, and strong, weak patterns. Basically, the time between these two flares is a bit longer than between these two flares. And also we see that this flare is stronger, this one weaker, stronger, weaker. So we have this sort of strong, weak, and long, short patterns which are sort of the main characteristics of these regular QPEs. And we have 3 candidates of such events. Then we have irregular QPEs, which show sort of these irregular signals. So there is no clear strong, weak, or long, short pattern. And we have approximately 4 candidates. Here, I'm showing all of the QPE candidates. There's 10 of them. So 3 regular, 4 irregular, but for the others, it's not really clear in which category they fall. And this is simply showing the duration of a flare as a function of the period between, sort of the time between the different flares. And yeah, we can see that the flares typically last a few hours, and they recur at intervals, let's say, from 2 hours to 100 hours. And these signals are characterized by peak luminosities between 10 to the 42 and 44 ergs per second. Now, regarding their spectra, this is what we see here on this figure on the right. So different colors correspond to spectra taken at different times. So the red line would be before the peak of the flare. The black one would be close to the peak, and then the blue one after the peak. Yeah, what's typical for their spectra is that these spectra show black body-like shapes with peak temperatures ranging between 50 to 250 electron volts. And what's also interesting is that harder bands show a faster rise and decline relative to softer bands. And also in the quiescence, so during this time between different flares, it's not like there is no emission, but there is some soft spectra present. So there is something else, at least a little bit going on in the galaxy. QPEs were detected in galaxies with supermassive black hole masses between 10 to the 5 and 10 to the 7 solar masses with redshifts up to 0.08. And what's also interesting is that 2 of these QPEs were detected in a galaxy where recently also a TDE, a stellar tidal disruption event, occurred. So this is also, it's hinting that there might be some relation between TDEs and QPEs. And this is also what we see here on this figure. So this upper figure shows light curve of one of these TDEs where the QPE was detected. These green scatter symbols and green lines and these pink ones correspond to detections of this TDE in UV and G bands. And this black one is also related to TDE measurements, detections, or observations, but in the X-ray band. While here, these scatter symbols, these correspond to QPE detections. So basically, these purple scatter points are actually the observations of QPEs, which are also shown here in these 2 lower panels. So what might be happening is that first you have a TDE, but then when the light of the TDE sufficiently decreases, you could start observing QPEs. But yet, there are still many things that we are not really sure about QPEs, and we only have 10 candidates. So yeah, there are likely a lot of things that we are not understanding. For example, we are not sure what really QPEs are. There's sort of a running joke in the QPE community that there are more models for QPEs than we have candidates. But yeah, roughly these different models fall into 2 categories. Something related to instabilities in an accretion disk, or that you have a supermassive black hole and then an orbiter. So another body close to the black hole that is somehow causing these QPEs. And I will briefly mention 2 models and then focus on the star disk collision model. So this model, disk tearing, this is related to the instabilities in the accretion disk. The idea here is that you can have an accretion disk and a black hole which is rotating. And then if the spin of the black hole and the angular momentum of the accretion flow are not aligned, you have length steering precession. Basically, accretion disk or accretion flow in the accretion disk will precess around the spin of the black hole, which can result in the warping of an accretion disk. and in very extreme cases, these different regions of the disk can actually break. So here we see snapshots from some simulations, and they show accretion disk breaking or tearing at the same time, just from different viewing angles. So what can happen is that accretion disk, maybe if you see here, can break into these sort of discrete rings which precess at different rates. And then these rings could sort of interact with one another, collide with one another, and this could give rise to shocks and could potentially explain QPEs. So this model could explain this periodic nature of QPEs, like for the regular QPEs, but the issue is that you need a fine-tuning of parameters. You need sort of the right properties of the black hole, and also modeling also the right properties of the accretion disk, which is not so clear to establish in realistic scenarios, let's say. Then another model involves a supermassive black hole and then a star which was brought in the proximity of the black hole due to gravitational wave radiation. And this star needs to be at the right distance from the black hole that it undergoes Roche lobe overflow during each pericenter passage. So basically the star is on an elliptic, mildly elliptic, eccentric orbit, and each time it approaches the pericenter, a fraction of the mass of this star will be stripped, will fall toward the black hole, collide with itself, and in these stream-stream collisions you could generate flares which would resemble QPEs. So this, again, this model could explain the periodic nature of QPEs, but the stability of such an orbit is questionable, because as soon as the star would get maybe a bit too close, it could be tidally disrupted. So this is also...
Why do you need stability? I mean, what's the longest time scale you observe this?
For QPEs? You mean for how long?
How long a single QPE is being a QPE?
Yes, so this is also not entirely clear. For a few years.
You can observe them for a few years now.
Yeah, there was one case, GSN 069. I think this was the one that was actually observed for the first one, the first QPE candidate. I think this one has been observed for several years.
And it's still active?
Yeah, I'm not sure about now, but at least 2 years ago it was, yeah.
Because my question is, did any of them stop with activity? You don't know.
Yeah, I'm not really sure about these all different observational properties, but yeah, definitely at some point it was visible and at some point it was not. Also during this period, during these 3 years when GSN was observed, there were some periods where it was not actually detected. But this could be like, if you have something happening in the galaxy, or in the center of the galaxy, which would generate more light than the QPE flares, that's why they could no longer be visible. For example, for this GSN, there are also some theories that that first you had a TDE happening, but then the star was not fully disrupted, and then the star was disrupted again, which could again obscure the QPE for a brief period of time. Again, we are not sure.
And they observed in X-rays with Swift or also something?
In X-rays, mainly with NICER and XMM Newton. And now the model which I'm working on is called the star disk collisions model. In this model, again, you have a star brought in the proximity of the black hole due to gravitational wave radiation. But the difference with the previous mass transfer model is that you have here some accretion disk. This star needs to be on an orbit inclined with respect to the accretion disk, so that during each revolution, it would collide twice with the accretion disk. And this could then generate QPEs. So not just to maybe give you a rough idea about the physical scales of the system that we are talking about here. So from the period of the QPEs can give you the constraint on the distance where these collisions are typically occurring. And these are then roughly 100 gravitational radii. Then assuming, for example, a circular orbit, mildly eccentric one, we can obtain the velocity, typical velocity at such distances of from the black hole, typical velocities of collisions, and we get about 10% of the speed of light. And then assuming radiation pressure dominated alpha disk model, we can get sort of the thickness of the disk, and they're pretty thin, so they are just a few stellar radii. And now a bit more in detail what is happening in these collisions. The idea is sort of this here, if you zoom in this region, this is what this inset is showing. So the idea is that when the star collides with the disk, it will heat up this gas inside the disk, which could then launch two outflows. So one in the forward direction and one in the backward direction. And these outflows are initially optically thick, but once they expand due to radiation pressure and their density decreases, we could start observing some radiation. Why this model is particularly useful or particularly promising, it's because it offers a natural explanation for this long-short pattern between different flares, right? So if you remember, for example, the period or the duration between these two flares is a bit longer than these two flares. And this can be naturally explained in this model if you have a mildly eccentric orbit of the star, because basically the star will spend a bit more time on one side of the disk than on the other, and the observer will likely see just one side of the disk.
But why does the star care to be on a nearly circular orbit? You would imagine that it comes from far away, and therefore eccentricity is close to 1, right?
Yes, but if I understand, if you have gravitational wave emission, right, then the orbit would gradually circularize. I think this is the idea here, yeah. And also this strong weak pattern. So this flare is stronger, this one weaker, stronger, weaker. This could be explained by the fact that the observer would once see the outflow sort of going in this forward direction, going along the same direction as the velocity of the star. And then here on the other side, the observer would see actually the backward outflow. So the idea would be that for example, if this forward outflow is a bit brighter, then the observer would see here a brighter flare and here a bit dimmer flare.
So Doppler boosting essentially?
Not necessarily here. I don't think you get sort of this magnitude in difference between the strong and weak flares, just assuming Doppler boosting.
But then wouldn't the ellipse be at any orientation? I mean, because here you have it a kind of symmetrical, I mean, perpendicular to the disk. And so you would have different collision velocities with the disk just because of this misalignment also, right? Yeah,
so this depends on the sort of how eccentric the orbit is. If it's mildly, okay, how inclined it is. Mm-hmm. Yeah, this could also be, yeah. And then irregular QPEs, so the ones that don't show this strong weak pattern or long short variation, they could, for example, be explained in this model by the precession of the orbit or the disk, again, due to lens steering precession, for example, that you could have that if the black hole was spinning and if the disk accretion flow is not entirely aligned, then it would precess a little bit, and it means that the star does not necessarily collide at the same distance and velocities, which could give then rise to these irregular QPEs. Okay, so this was more general about QPEs and the star-disk collision model. And now I will talk about the work that we are doing. And we are performing three-dimensional radiation-hydrodynamic simulations of star-disk collisions. We are using a flux-limited diffusion approximation for the radiation transport. So this is, let's say, a more basic way of treating the radiation in hydrodynamic simulations. And what we are doing is that we are not simulating the entire accretion disk, but we are just taking a small section, small local section of the accretion disk, like you see here. Basically, we take a cube of gas. We are doing simulations in a reference frame co-moving with the accretion disk, so this is not rotating. And also for the next few slides, I will show you results from the fiducial simulation. And for this particular simulation, the density of the disk is uniform. The density is given by this mass m0 inside the column directly intercepted by the star, which is 10 to the minus 7 solar masses. This is obtained from the alpha disk model. We are neglecting any gravity from the disk. We are also not considering gravity of the star. And also, this is also a sort of a simplified way. We're also constructing or treating star as a solid sphere. So basically, the interactions between the star and the gas are treated as elastic collisions. And for this particular simulation, we are taking the radius of the star to be equal to the solar radius and velocity of the star equal to 10% of the speed of light. Now, yeah, one more thing. We are expressing time just in these units of the crossing time, so how long it takes for the star to cross the disk. And maybe you don't see it here, but this color bar corresponds to the gas density in this case. So now I will show you an example of such a simulation. So we have a star which collides with the disk, compresses gas in front of it, creating a bow shock. Then a fraction of gas will start to be outflowing from the upper region. Fraction of gas will sort of flow around the star, collide here near the axis of symmetry, and this creates the backward outflow. Now the forward outflow, when the bow shock reaches the lower edge, sort of this radiation which was contained in the shock cap is suddenly released, and resulting in an outflow along the forward direction, which expands faster than along the backward direction. So basically, maybe a simple way of thinking what is happening here is that you have a star, it collides with the disk, and as it collides, it injects energy and momentum inside the surrounding gas. This energy and momentum are then redistributed, resulting in outflows along the forward and backward direction, which are clearly asymmetric in this case. So we see that the forward outflow extends to longer distances, meaning that it's faster, and also it carries more mass. And now I will show you another simulation. So this will be for the same simulation, except that I will be showing radiation energy density. In other words, also radiation pressure. So here, when the star collides with the disk, the radiation pressure suddenly rises. Then also in this backward secondary shock, we see that the radiation pressure is slightly higher. But then in these outflows, in the forward and backward outflows, the radiation pressure diminishes basically as the gas expands due to radiation pressure, and energy from radiation is converted to kinetic energy of the gas. Okay, so I already hinted a bit that this process can be understood by what's happening with the momentum and energy of this gas, and we will look at a few graphs sort of to see what is happening in greater detail. And here I'm plotting the momentum of the shocked gas along the z direction. So in our configuration, the star is moving along minus z direction. These values are normalized to some characteristic value p star. Basically, what's happening while the star is inside the disk, it continues to inject momentum. So this value is decreasing because momentum is being injected along minus z direction, just sort of due to our initial configuration. But then when the star leaves the disk, we see that this momentum asymptotes to a constant value due to momentum conservation. In this figure on the right, I'm showing the mass-weighted histograms of the specific momentum, basically Vz, so just velocity along the z direction. And these different lines correspond to distributions of gas at different times. So this blue line is at the start of our simulation. The green one would be when the star is close to the midplane of the disk. This red one would be when half of the star emerges from the disk, and this orange one is at late times, at the final snapshot of simulations. Basically, initially, this blue line corresponds to, we see that this doesn't have any bigger spread, basically because there is no shocked gas. But when the star collides with the disk and it injects momentum, this distribution spreads out, right? We see this green one. Then when the bow shock, so when this shock front reaches the lower edge of the disk along the forward direction, this radiation, which was trapped before in the shock cap, is suddenly released. So what happens is that when half of the star emerges from the disk, so this red one, is that you have this high velocity outflow, which is extending, which is causing this bigger spread in the momentum distribution. Basically, because you have this difference in which the forward and backward outflows are initially launched, the spread along the forward direction, so minus along the negative directions, is much bigger than along the backward direction. So this effect introduces a clear asymmetry. And also another thing is because these histogram distributions are mass weighted, this means that the area under the curves also gives us mass of the outflows. And we see that this area under the curve for negative values of Vz is larger, meaning that the forward outflow will have higher mass. So that was about momentum. Now let's take a brief look at the energy evolution. So we see here different energy components, total energy, kinetic, radiation for all the gas. The idea a bit similar than before. As the star is traveling to the disk, it's injecting energy, so this value is increasing, but then it asymptotes to a constant value. As the star is in the disk, also kinetic and radiation energies are increasing, but as the star leaves the disk, we see that this radiation energy begins to decrease, as basically the radiation energy is converted to kinetic energy through radiation pressure. Similarly, as for the momentum, also these energies are not distributed symmetrically. And this we see here on the figure on the right. So these solid lines correspond to radiation and kinetic energy of the forward outflow, and this dashed for the backward one. But the idea is that the radiation energy of all the gas will be split between the gas going forward and backward, and that this sort of split is not symmetric. The forward outflow will typically have higher energies and higher radiation and kinetic energies than the backward one. So all these effects are clearly showing that the physical properties in the outflows are different. This also means that the radiation transport in these outflows will behave a bit differently. So for these star disk collisions, for the conditions inside these systems, the radiation is transported via advection and via diffusion. Advection is more efficient in regions, in denser and faster flowing, faster moving regions, while diffusion is more efficient in regions with lower optical depth and that are moving with lower velocities. In this figure, we see luminosities, light curves, and these blue lines correspond to the total luminosity. The pink and the brown ones correspond to luminosities calculated just from the advection and diffusion flux, and the solid lines show the luminosities for the forward outflow, while the dashed ones are for the backward outflow. What we notice is that at early times, for example, if we compare this blue dashed and this solid line, we see that the asymmetry, or the difference between the luminosities of the forward and backward outflow is quite big. And this is because at early times, this is sort of how the photosphere would be at early times, where it would be located. And basically what happens along the forward direction is that advection is very efficient because you have this denser outflow moving with higher velocity. So this gives rise to this initial peak, and the reason for this asymmetry, larger difference in luminosities at early times. Then for later times, this is sort of the location of the photosphere. But basically what happens is that the forward outflow expands, the optical depth decreases, and we see that diffusion actually becomes the dominant source of radiation transport. While for the backward outflow, we see that diffusion is dominating basically at all times, because this backward outflow has lower optical depth and is also moving slower. So the outcome of this star-disk collision is of course affected by the key system parameters. So it will depend on the disk density, on the size of the star, velocity of the star, or inclination of the orbit. And I will just show you now two different simulations just to give you maybe a rough idea how these different system parameters affect the star-disk collisions. And first I will show you a simulation for a Gaussian disk, and then for a simulation where the star is on an inclined orbit. So in the case of a Gaussian disk, the density is the highest near the midplane and lower toward the edges. The star, as it travels through the disk, it will inject the same amount of energy momentum as before, as in the fiducial case. But one of the differences is that the outflow, which is ejected first from along the backward direction, will be less dense because these less dense regions are ejected, while along this forward direction, you still have first ejected this mass inside the cap of the shock. So basically in this case, the asymmetry in mass at least will be bigger than for the fiducial case. And then the other simulation for the star on an inclined orbit. So in this case, the star is traveling along a longer path through the disk. Basically, it spends more time in the disk. It means that it will inject more energy and momentum. Another difference is that the cross-section, basically the cross-section of the area that the star is affecting, is now no longer a circle, but it's an ellipse. So also these regions where the outflows are coming from are now elliptical, and they also have a bigger area. So in this case, the masses of the two outflows will be higher than for the fiducial simulation. Now, we were interested in seeing how does this asymmetry between the forward and backward outflow, so how does this difference in the luminosities change with different parameters. And we were interested in seeing if we can reduce this asymmetry to something very small, right? Because we saw that the luminosity of the forward outflow was always higher, but we were interested in seeing if we can reduce this. So an example of such a simulation is shown here. And what we see here, again, so this solid line is for the forward outflow, the backward for the dashed line for the backward outflow. We see here this early peak. This is again due to this advection-dominated regime which occurs early in the forward outflow. But we see that at late times, actually this luminosity of the backward outflow can be slightly higher. And what we argue here, because in observations, at least it was not, maybe in observation, it was not really clear if this early peak is present in QPEs or not. But what we argue is that this early peak could actually be missed, because observations typically don't happen like at a single time, but across some period. So basically, the observations are measuring light, in this case, for a few. I see Marusha is shaking her head. So
I mean, this is very contrived binning, right? Where you get this, like change your binning
Yeah. I mean, this is still work in progress. So if anyone has any ideas or something, we are open to any suggestions. But yeah. So here we are taking beams of 500 seconds. So it means that basically the luminosity is averaged across this time frame. And you see that, this early advection peak can be actually missed. So this, 500 seconds is...
You can miss it, that's fine, but you won't always miss it.
Exactly, yeah, but we have 10 candidates.
But none of them are showing those.
Yes, but also not all of them are that well observed. I showed some more well-sampled light curves. And also, it's not like we were thoroughly exploring the parameter space. We were just interested in, can we reduce this asymmetry as much as possible? But I agree. When you have more high-resolution observations, and if you don't observe this early peak, then this would be like a sign that this model, or at least, it's not working. I definitely agree, So, I think I'm nearing the end. Now, just to summarize briefly, we're performing three-dimensional hydrodynamic simulations of star-disk collisions. We found that as the star collides with the disk, it generates this nearly paraboloidal bow shock. And basically what is happening is that the star is injecting energy and momentum, which are then redistributed, resulting in outflow being launched along the forward and backward direction. But because these outflows have sort of different mechanisms of formation, this leads to asymmetric properties. The forward outflow will typically be faster and carry more mass. And also the radiation will be transported a bit differently in these outflows, meaning that also luminosities can be asymmetric. So we found that this forward outflow can exhibit a bright early luminosity peak, and this would be like a hint if this model is working or not. And we also found that this asymmetry between we argued that this asymmetry between the outflows can be reduced, meaning that this model could explain the strong weak pattern observed in QPEs. So that's everything I had in mind, and I'll be happy to take any questions.
So, any questions?
Okay, sorry.
We expect the star to lose momentum and energy with each passing, right?
Yes.
How many passings do we expect before we see a difference in the quasi-periodic exclusions?
Yes, so here I showed that sort of what is the, for some reason I can't go back. Okay, in any case, so the mass here in this column directly intercepted by the star is like 10 to the -7 solar masses, or maybe a bit more. So the star will not lose a lot of momentum. There were some simulations recently where I think they estimated the lifetime sort of the star before it gets fully ablated, and it was like 1,000 years or something like that.
I have 3 points. I mean, first, I understood that you have seen geometrically seen disks, right?
Yeah.
Okay. So these are alpha disk Shapura-Sunyara essentially, and in this disk, yes, what you showed, not the fiducial model, but the later one, the Gaussian, that's much more realistic because in vertical direction, these structures are not well constrained. They have a large corona atmosphere. Only slowly the density is falling off with the distance from the plane. So essentially, disks are not really confined in the vertical direction strongly, okay, especially the thick ones. So that's one point. The other point, and therefore maybe this initial and final shock are not so dramatic because the density is building up as you approach with the star. Yes, of course, you are much supersonic, but I mean, it's not so dramatic like having a vacuum and then coming into the disk. The other thing is, okay, Shakura-Sunyawa is completely unrealistic model unless you think what is the reason for this alpha, which should be 0.1 or something like that. And the reason is magnetic fields, of course. That's the only way out, as always in astrophysics when you're in trouble.
You add magnetic fields, exactly, yeah.
And magnetic fields mean that essentially the viscosity is driven by this ionized material in the disk and by the magnetic viscosity, okay? But then this magnetic viscosity, these large magnetic fields, if you assume that they are inherent to the material in the disk, so somehow frozen into this ionized material in the disk, then essentially maybe you can assume that the field lines are perpendicular to the disk. And if this is so, then this affects your outflow, because this material is for sure strongly ionized and it is not going ballistically, it is going along the field lines, because these are controlling the whole game, right? And so this would be maybe worth to consider
To explore.
in the simulation. And then just the final point, you said you have your regular cases and your quasi-periodic or whatever, okay? Well, your star, as we said, is, as you said already, is moving constantly across this disk, largely on a certain radii range, okay? And so somehow this disk is perturbed. I mean, there were many past collisions, years or decades or hundreds of years back, okay? And so at least in a statistical sense, it is not true anymore that you have a kind of axial symmetry about the density in the disk, but this is simply a record of the past collisions. So somehow stochastically in your simulations, maybe you can vary the density or maybe introduce some local gradients in the density which are not axisymmetric. I mean, and therefore you see how much of the variety of the whole thing you can get.
You can get just by slightly changing properties.
It goes through the hole, the other time it goes to the blob,
Yeah.
and you have a kind of intrinsic time variation. So maybe that's
That could also, yeah. Thanks.
I have a question that's connected to this. Would the star at some point, after many collisions, carve a hole in the disk, or does the disk come together before?
Yeah, disk should come back together. Now about the time scales, I think I would have to check, but I think the viscous time scales, or the times it would take for the disk to replenish themselves, is a bit longer than the characteristic period. Then again, yeah, you are not colliding at the same point because of some, let's say, apsidal or lens steering precessions. So I think this is not like a big issue.
Also, isn't the disk rotating as well?
Yeah.
So that's the same.
Ah, yeah, also that, exactly, yeah.
So you say you have 10 cases, right? You have many more cases where we don't see this periodicity, right, of accretion disks in nearby universe. So non-detections are also potentially important. So if you put your stars on generic orbits, can you explain the occurrence of this periodicity in a sense? Does it roughly make sense of how many do you see to be periodic and the rest of?
Yeah, I'm really not sure about this. I also don't remember any studies addressing this. You're asking just sort of what is analytically expected rate for these stars to come close?
Yeah.
Yeah,
For the stars to come close and cause the observable effect.
Yeah. Then again, it also depends which model you are trusting.
No, I think this.
Just the star-disk collision model, let's say?
Yeah. So do you have,
What
do
you
you
devote?
have enough stars on these orbits that you need in order to see this effect? And not too many, so you wouldn't, like, every single accretion disk would show this variation because we have stars in every single accretion disk, right? So is that roughly an order of magnitude?
Yes.
Statistics you're
So,
predicting?
yeah, you mean just from these 10 candidates, if you can infer some larger statistics?
No, you need to look at every single accretion disk we know of.
And then, yeah, I'm not sure about this.
Up to redshift 0.08 or
I think it should be, but I don't
And
remember.
what's the
Yeah,
number,
yeah.
Right? Do we have, how many do we know?
Well, the problem is also geometry, because you see accretion disk in this kind of closed regions only if you're looking down the funnels, right?
Okay.
Because otherwise you have the dust storms, which
Yeah.
is going.
But that is also giving you a percentage of where you will be.
Yeah,
able
and
to
then it would
observe.
be interesting to see what is the type of the central galaxy, because Seifert 1 and Seifert 2, the ones which are with reflection and the ones you're looking directly into the central engine, this would have some correspondence then, right?
Yeah, but
so just to check what are these 10 cases.
but also here you're not talking, mostly you're not talking about typical AGNs.
Aha.
Because in AGNs this was not detected.
Okay, so we are speaking also not.
Yeah,
about
you have to have very quiescent emission, so something.
But then, in this case, if we have a kind of, understand a kind of pristine accretion disk without dust storms around,
Yeah,
then it would be much more possible to have, I mean, a larger possibility to have it edge on. Because simply having a random orientation looking axis down is very improbable compared to being close to the equator. Right? And therefore your geometry in simulation should be largely from looking it quite edge on. I mean, I'm not saying 90 degrees, but okay, 60.
yeah.
Okay, sure.
So you mentioned the TD, possibly preceding this.
Yeah.
So what is the story then, that the TD creates a disk?
Exactly. The
But
TD creates.
The star is already on the orbit?
Yeah.
Okay.
Yeah, because in spiral of this other star, the one which will collide with the accretion disk, it's quite long, the time scale for this gravitational wave radiation. It's like 10 to the 6 years. So it means that such a star would likely experience, that it would likely be another TD occurring in this galaxy, because the time scale for TDs to occur in typical galaxies is like 10 to the 5 years.
So this is from the previous collision, the disk, I mean, something like that, from the tidal eruption event.
For example, yeah.
Yeah,
So
then the magnetic fields would be weak, and then alpha would be very low, right?
Probably.
Because in
Yeah.
star, you don't have much magnetic.
Yeah, exactly. Yeah. Yeah, it's more for AGNs, this
Yeah,
effect of the magnetic field. Yeah, right.
And then I saw on the slide explaining the TDE light curve that there is a delay when the X-rays emission occurs, right? That was 14, slide 14. Yeah, so there is a delay when the X-rays start shining. So this delay is when the disk builds up, we see the X-rays, or why is this?
Yeah, exactly. Typically, you see here initially more UV optical wavelengths. The idea in TDEs is that you might have some envelope, some outflow, which then reprocess this light from the inner accretion disk. But then as this outflow sort of dissipates, then the emission from the accretion disk would become more visible.
Yeah, but then why does the QPEs are quite late after this, right?
Yeah, so the light still, the idea I think here is that the light still needs to sufficiently decrease so that you would observe QPEs.
Okay, but they are anyways sort of happening already.
Yeah, already before.
Yeah, okay.
Could be.
Yeah, okay.
Or not?
Yeah, or not. Yeah.
Because, I mean, it seems to me that you just spot it.
Yeah, exactly. Yeah. This other star, the one that's colliding with the accretion disk, should already be present. It's just that the accretion disk was formed later.
Yeah.
But so we do see the start of QPEs.
That's the idea.
Yeah. I mean, they started the observations in NICER here. I guess if they started maybe a bit earlier, they could still observe them, but yeah.
I mean, there is no QPE where before a certain time we are sure there was no QPE happening. Like, was this object observed before the tidal disruption? Or?
I don't think so. because you don't know where to point your telescope. Yeah.
So it could have been possible that there were QPEs here, but
Yeah.
we were not
Yeah.
seeing them.
Yeah, probably, yeah. Because these QPEs are still not that bright. So one of the strategies that they're proposing now to find QPEs is that you first find the TDE, then you wait a bit, and then you check for QPEs. But yeah.
So how about Rosetta? Because it's scanning in the sky, right? Could you detect some of these guys in Rosetta data?
You have 4 of them.
Ah, okay.
So
Just search the Rosetta data.
yeah, Rosetta seemed really promising, but now there are some issues.
Okay.
How about Athena then?
Athena, probably, yeah.
It's
But
like
is it
decades
up and
of
running?
data.
Because I think
It-
it's off. I mean, I think it's off, right?
Yeah, I'm not sure, or if it's just because some disagreements with Russia, because they were a major contributor to Rosetta, right? Yeah,
Yeah, I think this.
it just stopped. Could be, yeah,
They
yeah.
stopped, but they have some data for about 2 years.
Yeah, for some initial period.
Yeah, Rosetta seems really promising, but yeah,
So what,
It
what's
is what
the
it is.
problem? What do you mean is the problem?
it's not working anymore.
Those guys are.
Yeah.
Okay, I think we should stop now. Thank you again for coming.
Thank you.